In Chapter 5, we are going to look at the definite integral. And in Section 5.1, we're going to look at estimating finite sums using LRAM, MRAM, and RRAM. Okay, if we take a look at a car that travels with a constant velocity of 75 meters per second from 3 seconds to 12 seconds, what is the total distance traveled by the car over this time interval? So here's the graph. Let's assume that this is at 75 meters per second, and this would be time 3 to time 12. And if we wanted to find the total distance, okay, well, this is a velocity time graph. And if I was to take the time from 3 to 12 and draw myself two vertical lines, I'm going to get some area under this graph. Now, if I calculated the area of this graph, okay, the area of the graph would be the height, which is 75 meters per second, times the length, which is 9, because 3 seconds to 12 seconds is 9 seconds. And then if I was to multiply those together, I would get 675, and the seconds would cancel, and I'd be left with meters. And that would represent the total distance traveled from time 3 to 12. So if I have a velocity time graph to find the distance or even displacement, I just find the area under the graph from a certain time interval. Now, that question was quite easy to calculate the area because the area under the graph formed a rectangle. But what happens if we have a graph like this blue one here and we're asked to find the distance traveled from time 1 to time 2? Well, now this is not a nice, easy geometric shape to calculate. So we're going to do what's called a rectangle approximation method. So RAM refers to rectangle approximation method. Okay, and here's our first example. Okay, so we have a object travels with a velocity of t squared from time 0 to 6. The velocity of the time graph is shown, or a velocity time graph is shown, sorry. And the question is asking us to use LRAM to approximate the area under the curve, which will approximate the distance. Well, the first thing I'm going to do is I'm going to join these dots with a smooth curve. Okay, and we are dividing, I'm going to divide my time into 6 intervals. So there'd be 1, 2, 3, 4, 5, 6. So each of those widths are the same width. And we are asked to use or calculate the left RAM. So what LRAM means is left RAM. And that means when I take each of my widths of my rectangle, I'm going to use the left edge to calculate the height of the rectangle. So my left edge of my first rectangle is right there. So if I draw my height, it's going to be at 0. From 1 to 2, the left edge is right there. So my height is going to be 1. From 2 to 3, the left edge is going to be 4. So that would be my third rectangle. From 3 to 4, my left edge would be at 3, and it would look something like that. From 4 to 5, it would go like that. And from 5 to 6, the left edge would be right here. And I would go across and calculate that area. So now I could calculate or estimate the distance by calculating the area under these rectangles. Okay, so the area is going to equal, the width of each of these rectangles is 1 second, times the heights. Well, the height of the first rectangle is 0, and this is in meters per second, plus the next height is 1 meter per second, plus the next height is 4 meters per second, plus the next height is 9 meters per second, plus the next height is 16 meters per second, and the last height is 25 meters per second. Okay, so if I was to calculate the total area, that's going to approximate the distance traveled from 0 to 6 using a left rectangle approximation method. So if I add up all of my different speeds, I'm going to have 55 meters per second. So I have 1 second, which is my width. times 55 meters per second. So this would end up being an approximate distance of 55 meters. Now we can see from the graph that this would be an underestimate because I am missing some spaces here where I didn't calculate the area. Okay, so a left rectangle approximation method for this particular graph gives us an under approximation of our distance traveled. Now, a right ram just means I do the very similar thing, except now I'm going to draw my rectangle, but now I'm going to use the right edge of my rectangles to generate my height. Okay, and why am I using right edge? Because it's asking for an RRAM, which means right rectangle approximation method. So from 0 to 1, 2, 3, 4, 5, 6, these are my rectangles. Now I'm using the right edge to get the height. So there's going to be the first height. There's going to be the second height. There's going to be the third height, the fourth height, the fifth height, and the sixth height. So this time, to figure out the area, again, my width of my rectangles is still 1 second. And the first height now is 1 meter per second plus 4 meters per second plus 9 meters per second plus 16 meters per second plus 25 meters per second, and the last one would be 36 meters per second. And now if I added all those up, I get a total of 91. So it would be 1 second times, just going to double check that again, 14. So yes, that is 91 meters per second. So if I multiply those together, I'm going to get 91 meters. And again, that would be my approximate distance. And clearly we can see that this is an overestimate because I'm calculating area above my graph. Okay? But that is the procedure for doing a right ram. Okay, in the last case, we're going to do what's called a mid-ram. And a mid-ram is we take the middle of each rectangle and use that to calculate the height of each rectangle. So here's my curve again. And now I'm going to break it up to 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6. Now I'm going to take the middle point of each of these rectangles, which is going to be 1/2. And this would be 3 halves. And the middle here would be 5 halves, 7 halves, 9 halves, 11 halves, and that would be all I would need for that. And then I'm going to use the heights from those points. So my first height would be somewhere there, which is going to be between 0 and 1. This height is going to be, if I go straight up from 3 halves, would be approximately there, and there would be my second rectangle. 5 halves, I'd hit about there, and I'll use that for the height for my third rectangle. At 7/2, I'm going to be somewhere up there, so I'm going to use that height for my fourth rectangle, and then 9/2 is somewhere up there, and 11/2 is going to be somewhere up there. So you can see now, these rectangles are a little bit more accurate for the total distance because I'm missing some area, but I'm also going above, and these areas are very close to each other. So what I miss by one, I gain, or what I go over by one, I miss in the other one. So it kind of gets to be more realistic to the actual distance traveled. So if I calculate the area now, again, the width of each rectangle is still 1 second. Now to figure out the actual heights, okay, I'm going to plug my value that I calculated the height of each rectangle into my function, which is t squared. So at 1/2, it's going to be 1/2 squared plus 3/2 squared plus 5/2 squared plus 7/2 squared plus 9 over 2 squared, and the last one was at 11 over 2 squared. And again, these are all in meters per second, okay? So now I am going to evaluate, so I'm going to get 1/4 plus 9 quarters plus 25 quarters, 49 quarters, 81 quarters, 121 quarters, and again, these are meters per second. And I would have to still multiply this by my value out front. So again, these are meters per second. My width of my rectangle is 1 second. So now if I calculate the area, I'm going to get 10, that's going to be 35 quarters plus 49 quarters plus 81 quarters plus 121 quarters. And that works out to be, if I left it as a fraction, it would be 143 over 2, which is approximately, if I change it to a decimal, it would be 1 second times 71.5 meters per second. If I multiply those together, my distance would be approximately 71.5 meters. And that seems to be the most accurate distance for this particular problem. So what we did is we just took the same example. We did a left ram, which we used the left edge to calculate the height of the rectangle. We used the right edge and the right ram, and we used the middle to calculate the height for a mid ram. Okay, let's take a look at a few AP examples. So here's an example from the 1998 exam, and it says the graph of a velocity function in feet per second of a car traveling on a straight road is shown from 0 to 50. And we're going to look at just question D here right now, okay? And in question D, they're asking us to approximate this. This is our integral symbol. We'll talk more about that later. But this really means, this integral, this means the area under the velocity graph from 0 to 50. And they want us to use a Riemann sum using the midpoint of 5 subintervals of equal length. Use correct units, explain the meaning of the integral. Okay, so we're trying to evaluate this integral. And this really just means right now the area under the velocity graph from t equals 0 to t equals 50. And they want us to use a 5 subintervals of equal length and use a midpoint Riemann sum. Well, we could use the graph, but we also have a table. So if we broke our table up into 5 rectangles, it'd be 0 to 10, 10 to 20, 20 to 30, 30 to 40, and 40 to 50. Okay, and so those are my 5 intervals. So my width is going to be 10 seconds. So the width of my rectangles are going to be 10 seconds. And now I want to find the middle of each rectangle for the height because it wants me to use a midpoint Riemann sum, or a midpoint rectangle approximation method, which is also referred to as a Riemann sum. So we'll talk a little bit more about that after, but a Riemann sum is a rectangle approximation method. So the middle of 0 and 10 is 5, so I'm going to use the height of 12 for the first rectangle. And the middle of 10 and 20 is 15, so I'd use the height of 30, and then I'd use the height of 70, 81, and 60. So on my calculation, it's going to be 12, 30, 70. This is going to be 12, and this is in feet per second, plus 30 feet per second, plus 70 feet per second, plus 81 feet per second, and finally plus 60 feet per second. And if we evaluate those, it should be 70, not 71. Okay, I'm going to add up all my feet per second. And that's 253. And if I times that by 10, my answer is going to be 2,530 feet. And what does that represent? Use correct units and explain the meaning in the context of the problem. Okay, well, that just basically means this is the distance traveled from, you must state the time, t equals 0 seconds to t equals 50 seconds. And that would be your final answer. Okay, I want you to pause the video and give this one a try. And just again, we want to do part A in this next example. Okay, hopefully you've had a chance to try part A. And in part A, we're asked to find again a midpoint Riemann sum with 4 subdivisions of equal length to approximate the integral from 0 to 24 of r of t dt. Again, this just means the area under the graph r of t from 0 to 24. Okay, now they want us to use 4 subdivisions of equal length, and they want us to use a midpoint Riemann sum. Okay, and now if we look at the table, we're talking about gallons per hour. It's a rate of water flow, and our horizontal axis time is in hours. So to find a 4 subdivisions, I'd be going from 0 to 6, 6 to 12, 12 to 18, and 18 to 24. So the width of my rectangles is going to be 6 hours. And now I want to again use a midpoint, so I take the middle of each of these to get my heights. So my first height is going to be 10.4 gallons per hour plus 11.2 gallons per hour plus 11.3 gallons per hour plus 10.2 gallons per hour. And if I add up all those values, 10.4 plus 11.2 plus 11.3 plus 10.2, that is going to equal 43.1. So I have 6 hours times 43.1 gallons per hour. And if I multiply those together, I'm going to get 258.6 gallons. And it says it wants us to use correct units and explain the meaning of the answer in terms of water flow. Well, basically, all that's happened is from time 0 to 24 hours, 258.6 gallons of water has flown through the pipe. So my statement would be from t equals 0 hours to t equals 24 hours, comma, 258.6 gallons of water flowed through the pipe. Okay, our next example, we look at the 2013 AP Calculus exam, okay, and we are looking at hot water dripping through a coffee maker, filling a large cup with coffee, and the amount of coffee in the cup from time 0 to 6 is given by a differentiable function where t is measured in minutes, and selected values of C of t measured in ounces are given in the table. In part A, we want to use the data to approximate C prime of 3.5, and they want to show the computations that lead to your answer and indicate your units of measure. Okay, so we're looking for the derivative at 3.5 in relation to function c. We don't know a function c, so we're going to have to do an approximation, a difference quotient, and 3.5 falls between 3 and 4. So it would make sense for part A to find the derivative at 3.5 be equal to c of 4 minus c of 3 over 4 minus 3. And c of 4 is 12.8. And c of 3 was 11.2, all over 1. And this would work out to be 1.6, and this was in ounces, and my time was in minutes. So the rate change at 3.5 would be 1.6 ounces per minute. And again, that would be an approximate because we used a difference quotient with 2 numbers on either side of 3.5. Now in question B, they want us to verify, is there a time between 2 and 4 at which C prime of t is equal to 2, justify your answer. So they're asking us, is there some place between 2 and 4 such that the derivative of t is equal to 2? And we're told that the function is differentiable and it is closed, so we know that the mean value theorem does apply. So mean value theorem applies as function is closed, continuous, and differentiable. And if you remember, the mean value theorem says that the derivative, and in this case, it is there a derivative? And the derivative would be c of t, such that the average rate change equals instantaneous rate change, and they want us to go from 2 to 4. Well, if I do the average rate change from 2 to 4, it would be 12.8 minus 8.8, all divided by 2. And if you work that out, I get 4 over 2, which is 2. So yes, there is a time between t equals 2 and t equals 4 such that c prime of t will equal 2, because the average rate change from 4 to 2 is 2, and because my function is closed, continuous, and differentiable, the mean value theorem applies, so there must be a place where the derivative equals 2. Okay, in part C, it says use a midpoint sum with 3 subintervals of equal length to approximate the value of 1/6 the integral from 0 to 6 ct dt. Okay. So for this one, we're not going to explain the units yet because we haven't really talked about what this means, but we can actually do the calculation for part C. So part C, they wanted us to approximate 1/6, the integral from 0 to 6 of c of t dt, which means the area under the curve from 0 to 6 of c of t, and then we want to times it by 1/6. So I can use the approximation, and they want us to use a midpoint approximation with 3 subintervals of equal length. So you have to read the question carefully. 3 intervals would be 0 to 2, 2 to 4, and 4 to 6. So the width of my rectangles is going to be 2 minutes. And I'm timesing it by the height of each rectangle. They want us to use the middle for the height, so we're going to use these guys. So it's 5.3, 11.2, and 13.8. 5.3 plus 11.2 plus 13.8, and these are in ounces. So if I do this calculation, okay, I'm going to end up getting 5.3 plus 11.2 plus 13.8. And that's ounces, and if I times it by minutes, I'm going to get 60.6 ounces minutes, which doesn't really make a lot of sense. But this 1/6, which will make more sense later, is actually in minutes. So when I multiply these, the minutes cancel. So 60.6 divided by 6 works out to be 10.1 ounces. And we'll talk about the meaning of this a little bit later on. Okay, so that's all I really wanted to do for the first, or for the this part of this question with the first 3 examples. Okay, now based on that, I'd like you to pause the video, and I would like you to try this question, okay, which is very similar to the last one, and I would like you to do this one as well. Okay, and you can check the notes online to verify your solutions to this one. Okay, so give those a try and see how you do, and we can take those up in class. Okay, and similarly, I would like you to try A and B from this question, okay, and see if you can come up with an answer to this one. Now, this one's a little bit unique because in this one, we're asked to find the area under the curve of 0 to 60 of the absolute value of v of t. So all that means is when you do your rectangle approximation, which in this case, they want us to use a left Riemann sum, if your area happens to be below the x-axis, it's considered negative area, but because it's an absolute value function, make all the area positive. And that might help you guide your way through that one. Again, we can look at those in class, and you can check the answers on the notes on the website. And the last one I want you to try is I would like you to try 3A and 3C from this question. So that's also going to be part of your assignment, and this is all in your handout package. And then there are 2 handout assignments which are posted in your, which I'll give to you to class, but here's the first one. Here's the second one in case you didn't get a copy of this assignment. There's the third question. And there's 2 questions there on Riemann sums. And here is the next one. Okay, so that ends the lesson. So hopefully you've had enough time to